Mike Davis. I'm a software engineer at DoorDash within our data platform. And today I'm going to be talking to you about how we're building a customer-facing analytics platform with Apache Pinot. And I don't have a Twitter account, but I do have these referral links here for our blog and for our jobs page. So feel free to check those out. Now, for those who are not familiar with DoorDash, we are a logistics platform that facilitates last mile deliveries where we're connecting consumers, merchants, and drivers in the most efficient manner possible. But another way to think of DoorDash is that we are a three-sided marketplace. We have consumers connecting with local merchants, merchants that fulfill the customer orders, and of course, Dashers facilitating that last mile delivery, completing that circle. And each one of these sides consists of a different set of users that engage with the platform with a dedicated application and to enhance that experience and get maximum value out of the platform. But today, let's dive into the merchant experience and see what are the goals of the merchants and what value does DoorDash need to provide. So during COVID-19, merchants were in survival mode, needed to prioritize survival and customer service over all other goals. So merchants needed to continue to generate profit to stay afloat, and they needed a way to connect to their customers that were no longer able to come into their restaurants anymore. And so they're looking for a way to provide that service. They also wanted to continue to grow and increase those sales. So they want to gain loyal and repeat customers, needed to expand their customer base. Maybe this is done by expanding their delivery radius, or maybe they're going to run some promotions to help acquire new customers that have never tried them out before. And they also need to continue to improve and iterate on the customer experience. So gathering feedback, periodically reviewing that feedback, maybe adapting their menu or iterating on new products or ideas. And all while understanding their sales performance through the use of analytics, identifying and addressing these potential issues. So to assist our merchants, DoorDash offers an analytics and operational portal that allows them to do just that. They want to measure and track their sales, adjust their menu on the fly, create deep understanding of their customers by tracking the trends and receiving timely feedback. And of course, want to continue to analyze their operational performance and meet the ever-changing demands from their customers. Now, the merchant portal helps to provide insight into historical sales, like how is my business performing today versus last month or last week? Are my totals, my total orders increasing? Am I tracking towards my sales targets? And if not, how do I increase my average order value? In addition to that, there are operational insights. So how can I reduce the overall wait time for an order? Get my product to my customers as fast as possible? Have there been any errors? Have we dropped any orders due to these errors? And how can we understand those, learn from them, and correct that going forward? And of course, cancellations. Maybe there was a recent spike. How do we understand that? How do we get notified that spike is starting to happen now and address that immediately and not finding that out days or weeks later? And of course, this all needs to integrate with the customer feedback loop, getting those really starting to improve our customer loyalty or assess your customer loyalty, understanding whether you're acquiring new customers or retaining existing ones, and what is their feedback. Maybe diving into some of that qualitative engagement and understand where I need to improve on a more one-to-one level, and also be more proactive and address these issues as they come up in real time. So what that amounts to is that the merchant portal is providing undeniable value. I want to double down on that by improving the overall experience. So when we initially focused on the needs of small merchants when the portal was incepted, and we had a small number of stores, maybe just a single geographical location. But as we grew, we needed to support stores with businesses rather with thousands of stores, and maybe those are geographically distributed. So their analytics needs, both on scale and dimension, are vastly different than the initial onset of merchant customers. And we also started to see scaling and reliability issues, both in the UI, but also primarily within our backend infrastructure that was more centered around a data warehouse. And we needed to provide bespoke corrections and fixes for that as they came up. So we knew that we were experiencing growing pains, and we're outgrowing that particular implementation, and needed to invest in an online analytical engine that helps solves not only the performance issues of today, but future-proofs us for the rapid growth that we're experiencing, and also addresses issues related to freshness that pure ETL just won't capture. So then, distilling some of those product requirements into more of a general set of analytics capabilities, we have the following goals. So for a better overall experience, we wanted to limit response times to no greater than 100 milliseconds. So we want extremely fast, ultra fast queries. And this is to encourage dashboard engagement and iteration. So providing a delightful experience through iteration and engagement. But that comes at the price of now might experience increased QPS. So we need to be able to handle an increased volume of an order or so magnitude of more requests due to that level of interaction. Again, this is customer facing. So we need to have high availability, no single point of failure, 24/7 operations. Now, to answer more questions, like for some of our enterprise customers, we need to support an increased level of dimensionality, more ways in which we can slice and dice the data directly within the portal. And also need to do so while providing finer grained data. So less reliance on pre-computed rollups, having access to as raw data as possible, to be able to see more trends that might get smoothed out with your typical roll-up based approach. And all this is leading to providing actionable insights, near real-time freshness of less than a minute from when an event or metric was produced. And in the future, we also want to start being able to surface anomalies so that merchants can take action immediately, maybe without even needing to engage the portal first. Start to surface actions that need to be taken. And these aren't requirements unique to the merchant portal. There are a variety of other use cases that we have at DoorDash that require the same stringent SLAs. And we want to deliver a self-service platform for real-time analytics and insight at DoorDash. So we want to enable end-user analytics capabilities with ultra-low latency. We want to be able to drill down and provide that iterative query support. And we also want to be integrating with our existing streaming pipelines in Kafka to provide that near real-time freshness. And of course, we always have batch and ETL use cases that we want to optimize for. So being able to improve the reporting experience through ETL is also a huge value that we need to add. And lastly, being able to not only provide that query interface, but be able to start to surface and monitor proactively on behalf of our customers and on behalf of our platform is something that we want to enable with high cardinality. Okay, so we evaluated several possible OLAP systems based on those pre-stated goals: Pinot, Druid, and ClickHouse. And I won't go into too much depth, but just to highlight some of the main points that went into our decision. And also just to state clearly that all these systems have been proven at scale. So that wasn't a question, but we needed to ensure that the operational model fit within the DoorDash ecosystem and was in line with our goals and feature support. So Pinot has advanced indexing support, including not only inverted indexes, but also JSON indexing, geospatial and star tree indexes, So ensuring that we can handle the needs of today, but also the future use cases as well as we continue to scale and we continue to onboard more and more use cases within the platform. And of course, it integrates well with our existing infrastructure being run on natively on Kubernetes and relying on S3 for sustained availability. Now, also Pinot has out-of-the-box support for multi-tenancy, so we wouldn't have to roll our own isolation semantics from one use case to the other. That's already built in, so that's another huge plus. Now, Druid is a very common solution to this problem and could solve many of our use cases, and it's also been well adopted, but the architecture is a bit more complex, requires more orchestration, more services to manage, and a little larger mental model needs to be taken into account. It's also well suited for semi-aggregated data, really leveraging those inverted indexes alone. And then ClickHouse was the last contender where we considered it for its OLAP and data warehousing capabilities. It is a very simple operational model, and you kind of think of it more in RDBMS sort of terms, and has leverages techniques of materialized views and whatnot for addressing some of those more complex use cases and addressing some of the roll-up needs and whatnot. But it kind of lacks some S3 support. It's also written in C++, which is great. It means it's extremely performant, but it is not constrained, and it's not constrained to the JVM. But at DoorDash, majority of our services run within the JVM, so we have a lot of firepower there, and so we're more encouraged to dive deep into systems based around Java in this case, and so we can really dive deep and hopefully contribute back to those systems. So with all those considerations, we decided to move forward with Pinot. So again, Pinot has been proven at scale. And we know it can handle our use case, but we still needed our own experience firsthand experience to fully understand the implications of our data set, the implications of our query patterns, and how to best model these within Pinot. And specifically, we wanted to understand the impact of indexing, segmentation, how that impacts request latency, the ability for the cluster to handle high QPS, and also under the constraint of a fixed number of resources. So we started with a simple cluster, 2 controllers, 2 brokers, 2 servers. And these are basically the minimum setup required for high availability. And we were able to deploy this quite quickly and easily with the open source Helm chart. So it made it easy to spin that up within our Kubernetes cluster. And so we set up our baseline. So this sample data set that we exported from our data warehouse, naive export from data warehouse into Parquet and S3, and imported that directly into Pinot. And we ran our simulation using just locus stress testing framework, where we gradually scaled up the request volume. And so we handled pretty well up to about just over 200 requests per second. Then from there, the request started to degrade a bit. We went from well under 100 milliseconds response times to now we're like teetering at a second response time. We still weren't experiencing any failures, but that performance degradation was definitely perceivable. But this was just a baseline. We're just establishing, okay, where are we at with zero indexing, zero optimization. And so the next step, of course, was then to introduce those indexes. So remember, our pilot use case is the merchant portal. So our queries are always in that context of a merchant. So in our data model, it means business ID or store ID. So those are predicates to all of our queries. So we then configured our sample table data set to use those inverted indexes and reran the simulation. Just one second. All right, here we're able to demonstrate that Pinot can handle that load from the simulation, which had a target of around 300 requests per second. And what amazing results on the client side. Pinot latency was stable throughout the test, well under 30 milliseconds in that P95 response time. Okay, so performance looked great, but if we took a look on the Pinot server side, we can see it was doing a lot of heavy lifting. So we're spending a lot of CPU cycles during this test. And so the next thing we looked into was our segment layout. So segments are the individual files or the individual collection of columns for a particular partition within Pinot. And I mentioned before, we did a naive export from our data warehouse into Parquet and into S3, but it was effectively unpartitioned. We just like scattered the data into like n number of files. And so we actually were experiencing a many small files problem. And so it's important to understand that when loading data from a raw data set into Pinot, it's a one-to-one mapping, like one file in, one segment out. There's no merging that happens. There's no compaction that happens during ingestion. All that has to be done upstream. And so in this particular experiment, we had over 100 segments that were being queried. So intuitively, we knew that this is not going to be efficient in leveraging those indexes. And since every one of these queries is going to have to peek into every single segment, look up within the dictionary the key mapping to our where clause, then from there grabbing the corresponding inverted index before then grabbing the underlying data to satisfy the query. So just a lot of churn within the segments. So the next step was to optimize our export by partitioning on the time dimension and actually compacting that. So explicitly saying, hey, all files for a particular day or for a particular week will be contained within a particular segment. And doing so, we reduced the number of segments to over 100 to around 10. And so now that we have a more efficient representation of our segments on disk, we then reran the test again to ensure no regressions. And to no surprise, the latency still looked great. We actually improved latency. That wasn't our goal, but it was a nice side effect. Now we're below 10 milliseconds in response time. And but again, we're already within SLA, but this is like icing on the cake here. But was dramatic was the impact on the server. So recall before we were seeing like 400, 500% CPU utilization. Now we dramatically reduced that. And a single server, one server was dropped by 5x, another was dropped by 10x. Less CPU with that deliberate segmentation strategy, which is a much more sustainable approach. So some lessons learned here. Indexing is critical. You definitely want to know your queries. Basic inverted indexes was all that we needed to meet the SLA that we established before running our test. But we didn't need to index on everything. Pinot is highly configurable, so you can choose to index as much or as little as you want. That's required for your use case. Also getting more custom tailored indexes, such as sorted index or geospatial index, and the JSON index is one I'm really eager to try out once that use case arrives is at our plate. And but also segmentation design should not be overlooked. If you're coming from a Hadoop world, you're already familiar with many of the small files problems, so similar guidelines apply. We actually reached out to Startree after discovering that we needed to focus on these segments to see what was the recommendation for size. And it came out anywhere between 200 megs to a gig. That's kind of the sweet spot to like leverage the index without being too big, where it's like too large of a segment to be loaded on an individual server. And we also Pinot will leverage the ability to prune segments, especially when partitioning on time. If your query is also confined with a particular time range, segments can be completely ignored, and only the ones that satisfying that particular partitioning will be included in the query, further optimizing the overall server utilization. And not just the size of the segments, but also understanding that the segments need to be consistently named, and that naming is kind of goes into some of the data modification semantics within Pinot. So if you're doing an incremental load or a full reload, or maybe you're doing more of like an upsert, you need to be aware of how that segment name maps to your new data versus your old. And so in a pure incremental world, you wouldn't want those segment names to overlap. But maybe you're doing maybe you're updating at a segment. So you would want to, in that scenario, to make sure your names do fully overlap. Otherwise, you'd be duplicating data. And so those boundaries should be well understood from one data set to the other, from one load to the other, to know that you're properly you're properly satisfying those particular segment level constraints. So again, Pinot doesn't have row level operations of deleting a specific row. That's all done out of band, where you generate a new segment with those rows pruned, and then update that segment within Pinot. GDPR requirements come to mind is a good use case for that flow. Okay, and again, without taking that in consideration, you might have data duplication or data loss. So it's definitely important to note. All right, so we mentioned before, one of the platform goals that we wanted to enable self-service. So we want to enable teams to not be bottlenecked with their implementation. We wouldn't, the data platform team, I guess another way to phrase this, shouldn't be blocking on adoption of other teams. And we wanted to have highly scalable and efficient autonomous teams onboarding onto the platform. And in our pilot use case, data was coming from our data warehouse. So we wanted to build a framework to easily extend any existing ETL and existing job and make that data set available in Pinot for query. And our ETL is pipeline. Our ETL pipeline is based around Python and using Airflow DAGs. So we implemented a Pinot mixin that any job can inherit, and so extending your job with this Pinot mixin class would automatically export your data to S3 after it was generated, and then initiate an asynchronous task to generate segments based off of those raw Parquet files in S3 and publish that data into Pinot. So that asynchronous worker fleet is a whole other cluster that's actually owned by the data platform, and again, it's responsible for performing those transformations from Parquet files, raw Parquet files, into columnar Pinot files with the proper indexes, and then pushing that metadata into to the controller API to make it available for query. So again, it's fully owned by the data platform. Other teams onboarding onto the platform simply just need to drop their data sets into S3 and then trigger this API. All right, now that we've benchmarked Pinot and we've established a corresponding ETL, start feeding Pinot regularly. Now it's time to go live. So going live for us meant 3 phases. We have a mirror phase, we have a disruption phase, and finally a rollout phase. And the mirror phase was implemented a dual read from the point of view of the backend service that would typically consume from either Pinot or data warehouse. So it was configured to do so. And that enabled us to, without any interruption, production interruption, service interruption, to start to measure latency between the two systems. But more importantly, we can compare the accuracy. So whenever onboarding a new data system, you want to establish parity first, and that's what we did. And also, while we're maintaining this mirror between legacy and the new Pinot based backend, we were able to confirm correctness and that the data that we were servicing from Pinot matched 100% with that of the legacy data warehouse. And while that was running, we're getting that confidence through an extended period of time with this live traffic. We also started to disrupt our Pinot clusters, really understand how any failures in a server or a broker or a controller, how that might propagate to our end users. So while we were monitoring that accuracy, the correctness, and latency, we introduced some of those failure scenarios to make sure all of those were well understood and mitigated those with before going live in production with the proper replication numbers, the proper number of brokers and controllers, et cetera. And then finally, after all that was done, we're ready to roll out. So progressively rolling out and surfacing the data that was generated from Pinot and phasing out the legacy data sets that was being surfaced from our data warehouse. And now customers are now reaping the benefits of the work that we've done. And at the end, of the mirroring campaign, we're able to roll out with confidence, knowing we have full parity between the legacy system and our new Pinot backend. And we also achieved much dramatically lower latency in the process, and also iteratively working with our BI teams so that they can continue to onboard and start to adopt more and more tables and onto this new pipeline. So in summary, customers need fast and timely analytics to improve their business. And Pinot can help address these needs with ultra-low latency responses of complex queries due to the advanced storage and indexing capabilities. Pinot has proven to be robust and highly scalable and highly stable at scale, making it suitable for web-facing analytics products and need high number of nines of availability in a 24/7, always-on world. And that last but not least, segment design is kind of the newer thing for us in adopting Pinot that should definitely be taken into consideration as part of the overall data model for maximum efficiency of your implementation. All right, thank you. And again, here's some referral links. So please check those out. And thanks for everyone's time.